A blast furnace is a high energy reactor that demands respect for its physical limits. So, today we are going to master the boundaries of our safe operating window. So, you will gain three deliverables. Uh, the first is the mastery of the detonation triad, recognition of pressure inversion triggers, and the forensic understanding of maintenance led failure chain. So, observe the blueprint, notice the blue line infrastructure and orange thermodynamic flow arrow. These are not just drawing, they are the boundaries between operation and asset loss. To manage these risks, we must first define the three distinct chemical vectors of the failure. Coming to our next slide, which is briefing on the triad of the blast furnace detonation. So look at these icons: gas air mixture, water gas knocking, and phase change vaporization. So the gas air vector ignite between 600 degrees centigrade to 700 degrees centigrade, and while hydrogen becomes volatile above a 5% concentration. The so what factor is synchronization. You cannot monitor just one. If your chemistry shifts, the kinetic shift instantly. So operationally, our only absolute defense is the rigorous separation of reactant to prevent the triad from completing. So these separation is maintained by internal pressure, which can dangerously invert during a sleep. So coming to the aerodynamic reversal and ignition. So on the left, green arrow shows noble positive pressure. On the right, look at the orange breathing mass. When this burden collapse, it create a 50-meter cube void, sucking in ambient oxygen indicated by red air ingress arrows. The so what is immediate. You are breathing air into a 700 gas mixture. We must manage burden permeability to ensure our safe yellow zone never transition into the catastrophic red zone. So beyond air ingress, we must monitor the chemical byproduct of cooling system failure, that is hydrogen. So now coming to the hydrogen activation curve. So during water injection, observe the hydrogen activation curve. The yellow line shows the 1984 spike where hydrogen hit 9%, well past the 5% knocking limit. Contrast that with the blue line where atomized spray kept hydrogen below 2%. The so what factor is the difference between the controlled cooling and a hydrogen bomb. Using direct water stream on red hot coke accelerate water gas kinetics. So we must mandate atomized spraying to keep our hydrogen level in the safe blue zone. While gas is a chemical threat, the physical expansion of water is equally lethal. So, coming to our next slide, which is on a volumetric expansion and trap phase changes. This is subsurface entrapment. When 1400 degrees centigrade molten metal seal a pocket of water, the steam expansion is 1600 times its liquid volume. The red arrow shows the incalculable upward kinetic force. The so what factor. Subsurface entrapment turns a simple leak into ballistic launcher. Whether it's groundwater or a failed slag notch, any moisture trap beyond metal is a detonation waiting to happen. So preventing these encounters require the atmospheric silt shown on our primary gases. So our coming to the next slide, which is about atmospheric silts and pressure management. So focus on these three gases. The first show our 500 Pascal minimum pressure limit, the safe zone. If pressure drop, the steam injection protocol must forcibly displace oxygen. Finally, look at the void inerting on the right. Areas like the bell hopper must be purged with the inert gas to break the triad. The so what is simple. These are not suggestion. Any alarm on these transducers requires an immediate automated response to prevent vacuum air suction. So these defenses are critical during the volatile phases of the operational transition. Coming to the control transition and the thermal limits. Transition or high risk zone. Look at the top igniting process. Flame at the stack head. We must deliberately burn off residual gas as it exits. Below, follow the blue arrows for the automation requirement. So we replace water stream with atomized spray to starve the hydrogen yield. Finally, ensure the stove burner shutoffs are secured. The so what is that most disaster happen during transition. If you lose that top flame, you are allowing gas to pool in a hot vessel. No procedural control can save a vessel that has lost its structural integrity. Coming to the structural integrity as a prerequisite for the safety, so look at the red zone on the shell diagram. Pushing a compound past its design life causes thermal fatigue and brittle cracking. The so what is a hard truth for management. Spraying high pressure water externally onto a cracked cell accelerates fatigue. It doesn't stop it, it actually deepens the rupture. Operationally, you must advocate for realigning based on the forensic cracking data, not just production quotas, to avoid a total structural collapse. So when structural integrity is ignored, the result is a deadly, predictable chain reaction. So let us discuss on autopsy of a structural collapse. So this flowchart shows the autopsy of a collapse that took 19 lives. It started with a delayed reline uh, leading a 75% cooling damage that led to water ingress, then thermal runaway, and finally aerodynamic reversal. The so what factor is that this was a predictable chain reaction. Sucked in air, explosive gas, and a brittle shell equal total structural vaporization. This is the price of ignoring the telemetry we have discussed today. This same chain of errors applies to external systems like our dust catchers. So let us go through a case study, the 1959 dust catcher ignition. As you can see, the red explosive position in this downcomer highlight a procedural disaster. A 3-hour delay in reignition allowed gas to pull, while a broken steam valve eliminated our inerting shield. When they reignited, the detonation was instantaneous. The so what factor, a 3-hour gap in a high energy system, is an really big. So this teaches us that maintenance of safety equipment like a steam valve is just as vital as uh, the production hardware itself. So, finally, we must respect the dangers of transporting molten metal across the plant. Coming to this case study on subsurface entrapment in transit. So as you can see, panel 1 shows a minor leak into torpedo car, panel 2 shows the poor sealing that water, panel 3 the agitation, moving the car shifted the metal, triggering a steam blast that launched a 1.25 ton nozzle 21 meter into the air, 80 tons of metal rained down. The so what factor, a torpedo car is a mobile pressure vessel. So movement is the trigger. Try must mean the entire transport chain from the runner to steel shop. We conclude with our operational directive, the limits that keep our crew alive. So let us discuss on those control limits, and those are always written in blood. So the physics of iron making and unforgiving situations always there. So we conclude with three absolute directives. Never drop pressure below 500 pascal. This is number one, without a steam inerting. Okay, so we must have to have a steam inerting. Monitor hydrogen relentlessly during the blowdown to stay below 5%, and never treat a relining schedule as a negotiable economic efficiency. So look at that glowing red sensor. It represents the discipline required to stay alive. So these lessons are written in blood. So let's respect them on our watch.